Hello everyone. Today we're going to be looking at derivatives. So we're going to be looking at the geometric as well as the physical interpretation of a derivative. So before we get started with the definitions, let's look at the notation of a derivative. So a derivative can be represented by d over dx or f prime of x. We're going to look into notations a bit more later on, but for now, let's start off with geometric interpretation. So let's say we want to find the tangent line to f of x at point x0, y0. So x0, y0 is a fixed point in f of x. So let's draw a graph. So this is my y-axis, and here's my x-axis. And let's say I have a exponential curve. The exponential curve. And then I have a fixed point P here at x0, y0, right? So the tangent line intersects the function exactly once. So it looks something like this. So the derivative is basically just the slope of this tangent line. So if you remember the point slope one, it states y minus y0 is equal to m times x minus x0, where m is the slope of the tangent line, which is this, and we call this the derivative, or f prime of x, which is just derivative. So if we look at formal definition wise, so f prime of x0, which is the derivative of f at x0, is the slope of the tangent line to y equals f of x at point P, which is x0, y0. There's your formal definition of a derivative. So now, imagine, let's redraw this. Let's take this graph again, actually. So let's say I have another point, Q, over here, and I have a secant line that intersects this graph. So it would be like this. So it intersects the function twice. So this secant line, what happens is, as this secant line approaches the tangent line, as in the slope of the secant line approaches the slope of the tangent line, so it converges like this, it goes this way, the secant line will eventually become the tangent line. So let's write this down. So as point Q approaches point P, or gets closer to it, the slope of a secant line will get closer to the slope of the tangent line. All right? So let's look at this diagram again. It's more spaced out this time. So we haven't defined, we said a tangent line intersects a function exactly once, but we can also call it the limit of secant lines, PQ, as Q approaches P, where P is a fixed point. So let's look at a different diagram now. We'll explain this definition in just a second. So let's say I have x0 here, and then I have another point here. We'll define it in just a second. And then I have my point P here, and then I have point Q here, right? So when we say the secant line point PQ, it's going to look something like this. And if you look before, the secant line point PQ will intersect the function exactly twice, because both points are on the function. So let's define, we already know this point is x0 and then f of x0, right? And this distance here is the change in x. So we will denote this as delta x, which stands for change in x, right? I mean, a point P is at x0 and f of x0. right? So this would be change in the function, right? So delta f, change in the function. So, and this point would be x plus delta x, comma, f of x plus delta x, right? So if we look at the slope here of the secant line, rise over run, you're going to see it's delta f over delta x. So this is the slope of secant line PQ, right? Slope of the secant line PQ. So what happens is the slope as the change in x, what we call this limit, approaches 0. So as delta x approaches 0, as the change in x gets smaller and smaller, q will approach p. And eventually, the secant line that we saw before, this, will eventually become the tangent line. So m, the slope of the tangent line, is the limit as the change in x approaches 0 for delta f over delta x. And this is the slope of the tangent line. We can rewrite this equation because, remember, the slope is going to be delta f over delta x as delta x approaches 0. So we can call the derivative f prime of x 0 to be the limit as delta x approaches 0 for the change in y over the change in x, right? And the change in y is simply f of x plus delta x minus f of x 0, right? This is x 0. So it's going to be f of x 0 plus delta x minus f of x 0. So this is the change in y over the change in x is just delta x. And this, we call this the difference quotient. So now let's look at a problem and keep this difference quotient in mind. So let's say I want to find the derivative, let's say I have the function f of x equals 1 over x. And I want to find the derivative of this. So remember let's draw a diagram out first. So that's my y-axis, and this is my x-axis. And the graph will look something like this, a hyperbola. And if I have point P here, it's going to be at x0. The tangent line will look something like this, right? So if you remember from before, the derivative is simply just delta f over delta x, right? So in this case, so if we just plug it into this difference quotient up there, this is simply just going to become, so f of x0 plus delta x is just 1 over x0 plus delta x. And this is just 1 over x0, all of that over delta x, right? So let's factor out the 1 over delta x, and let's create a common denominator for this over here. Let's create a common denominator for that. So the common denominator would just be x0 plus delta x times x0. So this is just going to turn out to be x0 minus x0 plus delta x over x0 plus delta x times x0, right? And what happens here is this cancels out, so we're left with negative delta x over x0 plus delta x times x0. Remember, this is 1 over delta x from before, so the delta x cancels out now. So we're left with negative 1 over x0 plus delta x times x0, right? So now if we bring it here, if we take the limit as delta x approaches 0, we get, so imagine delta x as being 0. This just turns out to be -1 over x0 squared, right? X0 squared. And this is going to be f prime, or derivative of x0. And this makes sense because our slope is negative here. And if you look at the tangent line, it also has a negative slope. So now let's look at some more notations for derivatives. We looked at f prime of x, which is also equal to, we can call it df of d of x, or dy over d of x, or d over dx f, or d over dx y. Now, all of these represent the exact same thing, right? They all represent a derivative. This is called Newton's notation, and these are called Leibniz notation. Now let's look at our final problem for the day. Let's say I have the function x to the n, where n could be any natural number, right? So we need to find the derivative of x to the n, right? So if you remember the difference quotient from before, delta f over delta x, well, this is just going to equal to, you remember from before, f of x0 plus delta x minus f of x0 over delta x, right? So we get x plus delta x to the power of n. That's f of x plus delta x minus x to the n. That's just f of x over delta x. Delta x. So before we try to solve this, let's look at a quick side lesson. Let's look at something called binomial theorem. Now, binomial theorem basically is let's say I have a function x plus delta x to the power of n, right? So this is a binomial taken to the n power. And what we basically get is this is just x plus delta x times x plus delta x, so forth, n times, right? N times. So this just happens to equal to, well, not happens. This is equal to x to the n if you multiply every x in this long chain, plus, let's say I take one delta x and multiply by every other x, right? So I could take this one delta x and multiply by every other x, or I could take this one delta x and multiply by every other x. We get n of these because each delta x can be multiplied n times because there's n delta x's, right? And we're multiplying it by x to the n minus 1 x's, right? So this is that. And the rest of it we don't care about. We'll call it chunk. This is for any terms with delta x having a degree of 2 or greater. Now we will see why that doesn't matter in just a second. So if you have delta f over delta x again, that's equal to, we could factor out the delta x. And now this is equal to x plus delta x to the n power minus x to the n. And that's just equal to x to the n plus n times x to the n minus 1 times delta x. Basically what we saw here. And then minus x to the n plus chunk. And then what happens here is x to the n cancels out, and we're left with 1 over delta x times nx to the n minus 1 delta x plus chunk. Also, the notation for this chunk is O of delta x squared. It basically means any term with delta x having a degree of 2 or greater, and we don't care about that. We'll see in just a second. So this delta x cancels out, and this turns into O of delta x. So any term with delta x having a degree of 1 or greater, and we get nx to the n minus 1 plus this, and if we take the limit of this as delta x approaches 0, we get nx to the n minus 1, because this is just 0, and we only have this left. And this is the derivative. So d over d of x of x to the n is n times x to the n minus 1. And this, we call this power. And it extends to every polynomial. So for example, if I wanted the derivative of, let's say, 3x cubed plus 4x squared plus 5x, what we do is we multiply the degree by the coefficient and subtract 1 from the degree. So this turns into 9x squared plus 8x plus 5. And that's the derivative of this. So I hope you enjoyed this video, and thank you for watching.